Hi, so in this video I'm going to show you how you can use matrices to find pupils, stops and windows. Now these are very important aspects of standard optical systems. When you're designing optical systems, they are vital for designing for the right amount of light, for the right amount of image that you're trying to form, for the kind of objects that you're looking at. This is also to kind of support the assignment that went up a little while ago, where you can actually try and calculate some of these. But in this video, I want to introduce what these terms mean and how you can use the matrix method to analyze them. So right at the beginning, we said the whole point of using a lens rather than, say, a pinhole camera to form an image was that with a lens, you can gather lots of light from every single point on the object in order to create the image. So what we're going to look at in this video is exactly how much light do we gather for particular situations. So here I've got a fairly straightforward two-lens system. It's got two positive lenses, one with 28mm focal length, one with 26mm focal length. They both have the same diameter, they're both 40mm across. And on the left-hand side here, I've got a small object, and I'm forming an image of it over here on the right-hand side. So if we look at the rays of light that come from, say, the center of this object over here, they are going to pass through the series of lenses, and there is a certain maximum angle that they can form to go through this lens. So, for instance, if this is the sort of maximum ray that can go in the upwards, and this is the maximum ray that can go in downwards, they form like this kind of triangle. We've got rotational symmetry, so this is really a cone. So every point on the object, a cone of light rays can enter the system. The object, of course, is giving off light in all directions. So the bigger this angle, the more of that light we're capturing by our system. Now, you can see this angle here is defined, or the size of this cone is defined by two things. This angle, but also the base of the cone is this first lens. So this first lens is limiting how much light can go into this system and go through the whole system. So if I choose a smaller lens, same focal length, I'm still focal length 28, but now I've reduced my diameter to 20mm. Nothing else changes. The magnification of the object doesn't change. The position of the image doesn't change. All that's changed is the size of this cone of light. So by reducing the size of this lens, I've reduced the cone of light. I'm letting less light into the system. So I can increase that again, make it bigger. How big this cone is also depends somewhat on the image. So if I move my object back a little bit, the image forms in a different place. I get different magnification, but also if you look, this cone angle has changed. So where the object is also going to affect how big a cone of light we manage to capture by the system. Okay, so now this angle that we produce here gives a very important quantity which is used to kind of quantify how much light an optical system gathers, and it's called the numerical aperture. And basically equals the refractive index times the sine of this half angle of the cone. This is the half angle of the cone, not the full angle. The reason the refractive index is there is because the refractive index of the material in which the object is also affects this cone of light. Because it affects the refraction at the surfaces. So let's make this even bigger now. Let's change these lenses up again. I'm going to make the first one bigger and the second one smaller. Again, we've kept the same focal length, we're still forming the same image. Now, if you look at this situation, the ray that leaves this and goes to this point on the first lens clips the edge of the second lens. So now the second lens is limiting the amount of light that can get through the system, not the first lens. We've made the first lens really big, we've made the second lens smaller. And if you look at this steeper ray, this ray gets through the first lens, but it doesn't get through the second lens. So now the second lens limits the amount of light. So in a complicated system with many, many lenses and apertures and other things in it, the element that limits the amount of light is not necessarily the first one the light comes to. Whichever one it is called the aperture stop. So the individual element within any optical system that limits the amount of light going through is called the aperture stop. And that could be a lens, it could be a mirror, it could be a prism, it could be any item that you put in the optical system. It could also be an actual aperture, so a plate with a hole in it or an iris that you use to control the aperture. So the aperture stop is very important, and you can see we can choose which element is the aperture stop by choosing the size of the lens. So in this case, the front lens is the aperture stop. In this case, the rear lens is the aperture stop. Okay. Yeah, so now if you were to take this optical system with the aperture stop on the second lens and look into the front of the lens, of the front lens, you would see the second lens through the first lens, and you'd see it as a little hole, but you would be looking through the front lens. And because you're looking through the front lens at the second lens, the size of the second lens will appear different. That image that you see of the second lens, of the aperture stop, is called the entrance pupil of the system. And the entrance pupil serves a very important purpose. Every ray of light that enters the system must be angled to pass through the entrance pupil. So the entrance pupil is not a real thing. It is the image of the aperture stop. It could be in front of the first lens. It could be behind the first lens. It could be the first lens. So the entrance pupil could be anywhere depending on the rest of the optical system. And what it is the image of the aperture stop in the elements before it. So the rays of light act or go into the system. The maximum ray of light that can go into the system goes in as if it was going to go through the entrance pupil. So that cone of light, the accepted cone of light by the system, has its point at the center of the object, and its base is the entrance pupil of the system. The ray that does this, the ray that goes from the center of the optical axis of the object and is angled to hit the edge of the entrance pupil, is called the marginal ray of the system, and it defines how much light we are gathering from the system. If the lens at the front of the system is the aperture stop, so the front lens is the controlling aperture, then that front lens is also the entrance pupil. Okay, so the entrance pupil can be the front element. If the front element is not the aperture stop, then it could be in front of or behind the first element. So the entrance pupil, you have to calculate where it's going to be, and we're going to work out that later. There is also an exit pupil. So that's the image of the aperture stop looked from the other direction, looked from the image side of the system. So if we looked into this set of pair of lenses from this side, from the image side, the aperture stop, which in this case is the first element, would appear to be here. Okay, and again, all the rays of light that leave the system have to pass through the exit pupil on the way out. Now, in optical design, the exit pupil is very important, particularly for systems that you are looking into, because your eye is itself an optical system. And in order to connect those two optical systems together, the entrance pupil of your eye, which is your actual pupil, has to coincide with the exit pupil of the system that you're looking at. If it does that, then all the rays of light that leave the system will enter your eye. If the entrance pupil is too small or is in the wrong place, either you will get a very dark image or you will not get the entire image into your eye. In optical design, they usually make it so the exit pupil is a little bit further away, a small distance away from the lens that you look into. That's so that you can comfortably put your eye in this position without having to press your eye right up against the system to look. So microscopes, telescopes are designed to have an exit pupil that is a short distance away from the eyepiece lens. Another example is gun sights. In gun sights that you're supposed to look into, they make it so the exit pupil is quite a long way away from the last element of the sight, because when the gun goes off, you don't want the sight to smack you in the face as the recoil goes. So there they make the exit pupil a long way away. So generally, if you're connecting together optical systems, you connect them together so that the exit pupil of the first one coincides with the entrance pupil of the next one, and so on down the chain, so that you can get light through all the systems with the same efficiency. Okay, so this aperture stop controls the amount of light that comes from each object point, but it doesn't control how much of the object you can see. To see that, we have to look at the rays of light which are coming not from the center of the object, but from the extreme edges of the object. So when we look at these rays are called the chief rays, the rays that come from the extreme edges of our object. They are angled to go through the center of the aperture stop. Now, each individual point of light on the object is producing a cone of light, and the size of that cone is more or less the same for all of them, and that's controlled by the aperture stop. But the center of that cone must go through the center of the aperture stop. So if you trace those rays, you will see that they can go all the way through the system. They go through the aperture stop, in this case is the first lens, so they go through there. They go through the center of the exit pupil on the way out to form the image. But as you can see, they clip the edge of this particular lens, the second lens. If I was to try and look at an object further away from the axis, that ray of light would miss the second lens altogether, and so I wouldn't see it. So this particular lens in this case is limiting how far away from the center I can see objects through this system. The element in the system that does that is called the field stop. And the field stop limits the amount. And again, I can change the size of the field stop. If I chose a bigger lens for this, I could see more of the object than before. So here's a small field stop. I see just my object. I increase the size of the field stop. I can see parts of the scene beyond the edges of this particular object. So notice that as I change the field stop, it doesn't affect the aperture stop. So it's not going to affect the amount of light coming in for each individual point, but it is going to affect how much of the scene I can see. Okay, so the field stop is the element that limits the amount of light that can be seen. And I can change both of these independently of each other. I can change the size of the aperture stop at the front there, and that makes the size of the cone coming from each point bigger or smaller. Or I can change the field stop size, and that affects the size of the scene. So These two things together allow me to control the amount of light that's coming through the system and the amount of and the size of the scene that I'm looking at. So if I have this particular setup, as I mentioned, there is light coming from every point over here, not just this one lens. So if I turn on all of those rays and use a slightly bigger lens in this case, what you can see is that from this point over here, which is a little bit beyond our object but still in the scene, we have rays with a cone just like the ones from the center. A nice wide cone of light rays come from this point. They go through the aperture stop, fill the aperture stop. They form together again here, so we've got another image. They go through the field stop, they go through the exit pupil, and they form on the image at the end. So what you'll see though is that here at the edge of the field stop, some of the rays aren't making it. There are still rays making it, so I will still form an image of these points, these extreme points over here at this side, but less rays of light are going to make it through because some of them have been clipped by the edge of this image. Now what does that do? Well, it doesn't clip the image, it doesn't cut things off the image, but it does mean that these points at the edges of the image receive less light than points near the end of the image. And that produces an effect called vignetting, which you can do on purpose for artistic merit. But if you were trying to, for instance, take careful measurements of the amount of light coming off a scene in a microscope, you may be trying to do fluorescence measurements from a biological sample, it's very important that you're collecting light equally across the whole system. So here on the right, you can see a scene taken where vignetting is happening, where some of the light at the edges of the scene, less light is getting through because it's being clipped by the field stop. Here we have an unvignetted scene. You can see that it's like uniformly illuminated across the whole surface. So one way they can get rid of that is that you can deliberately put in a field stop. So in this setup, it's the same pair of lenses again. In this particular setup, instead of letting that second lens be the field stop and limit the size, I've deliberately put in an aperture. So the aperture could be a fixed thing, so a plate with a hole in it, or it could be an iris that opens and closes like the iris of your eye. And I've placed it exactly here at one of the intermediate image points. So this is where the image from just the first lens is formed. And what happens here is all the rays of light from a particular object point come back together at a point at this place. So when I put the field stop in here, any ray of light from an object point passes that edge, then all the rays of light from that point will. So although this will reduce may reduce the size of the scene, we've got rid of the vignetting, so every single point will receive the full amount of light that gets through the aperture stop. So deliberately putting in a field stop can do that, can allow you to produce an image without vignetting. One thing that you'll notice here is we have two more images, and just like the images of the aperture stop are the entrance and exit pupil, so the images of the field stop are called the entrance and exit windows. These windows are the images formed by the lenses before or after the field stop, and they frame where in the real world the image is actually coming from. And so you can see here this limits the amount of light, the size of the image that we get. So all rays of light that can go through this system have to go through two things. They have to go through the entrance window and they have to go through the entrance pupil. And on the way out, they have to go through the exit pupil and the exit window. So you can see here all the rays of light go through my exit pupil and they will end up over here on the exit window. Now, in most cases, if you're using like a digital camera or some kind of digital sensor, the thing that is your field stop is actually the sensor that you put at the end. So you design it so the image fills a whole big plane here like this, but your image essentially is limited by the size of the sensor that you put actually behind the lens. Okay, so those are, to summarize that, we've got two important things. Oh, and just really quickly, I have put in here a deliberate aperture stop. So I can, as well as controlling the field stop, if I put in a deliberate aperture, I can also control the light directly. So if you've got a fancy camera that can control an SLR that can control the amount of light going through, what it has is an aperture stop, physical aperture stop, that can open and close and change the size of the cone of light that comes through. So if you look at this system, so this is the full kind of system going from front to back. Points of light start here on the object plane at the edge of the entrance window. They come through the lens. How much gets through is limited by the real aperture stop here, and behind it is its image, which is the entrance pupil. So if you look at the cone of light going into the system and trace that along, you can see that is angled to go through the edge of the entrance pupil, and the other one down here through the edge of the entrance pupil. It's then focused so that it actually goes through the aperture. It comes to an image here where we also put the field stop. Comes to the second lens, they all go through the exit pupil and they form the image over here. So the entrance window and the exit window are the images of the field stop. The exit pupil and the entrance pupil are the images of the aperture stop. And we can control these things independently. So for instance here, I can control my aperture stop. So I'm not changing my field of view, I'm just changing the amount of light that goes through into my system. And I can use that then to control my illumination. I can make it really, really small, I can make it really, really big. And you can see that as I move that, the entrance window changes size as well. Entrance pupil, changing size as well. And I'm changing the cone, but I'm not changing the size of my image. I can change the field stop independently as well, whilst keeping the I can change the field stop whilst keeping the aperture stop the same. So I can make it a bit smaller there, and then I kind of clipped off some of my object that I was interested in. I can make it bigger. One thing you have to be careful of though is that if you make it too big, as I've made here, I've started to clip some rays again off the edge. So in this case, I'm going to have vignetting again. I can adjust that by adjusting the aperture stop again. So here it's slightly vignetted. Here I reduce the aperture stop and all the rays are getting through. So generally vignetting is a problem when you have a wide field angle like this and a large aperture stop. So particularly big fisheye lenses, big wide angle lenses can have problems with vignetting if you have a big aperture stop. Okay, so how do you actually find which element is the aperture stop? Because obviously there are lots of elements. Sometimes there can be dozens of elements within an optical system. How can I tell if, for instance, this second lens here is the aperture stop? Okay, well, so to find the aperture stop, I need to look at rays of light that come from the object and start on the optical axis. So they're going to have a vector, a ray vector, where the height is 0 and the angle is some angle, and which we would like to find out. And we know that's going to end up at the very edge of this particular element. I want to know what angle do I have to launch light into this system so that it ends up just at the edge of, say, this second element. So I know the diameter of my second element, so I also know the radius of my second element. It's also going to have a particular angle when it gets here. I'm not too interested in that angle. So how do we've got this input ray and we've got an output ray. There's only one thing we actually know here, which is the radius of this. But we also know all the elements in between. So what we can do is look at ray tracing this. So in order to get to this second lens, this ray of light has to pass over this distance, go through this first lens, and then pass over a second distance. So what I could do is I could work out what that matrix is for the point from here to the second lens, to the lens that I'm interested in. So my transfer matrices would be, there'd be a translation matrix for this first L1, there'd be my matrix for my first lens, and then there'd be another matrix for my distance here. And that is going to give me an ABCD matrix, a 4-element matrix, that describes how rays of light go from this point to this point. Notice that I have not included the focal length of the second lens because I want to know when the ray just reaches the edge of it. I'm not interested about it going through the lens. I want it to just hit the edge of it. So once I have this ABCD matrix for every element from the object to the element of interest, I can look at my ray tracing matrix. So I know that if I take this this ray from the optical axis and I put it through that matrix, it's going to end up here at R alpha 1. So if I do that multiplication, so this ABCD I can calculate from my distances and focal lengths. My A0 I don't know, my R I do know, but let's do this multiplication anyway. If I do this matrix multiplication, I'm going to multiply A by 0, I'm going to multiply B by alpha 0, and then I'm going to multiply C by 0 and D by alpha 0. I'm going to get this. R alpha 1 equals B alpha 0 over D alpha 0, where B and D are the elements of that matrix that I can calculate. So you can see that R is actually going to be equal to alpha 0. So I can solve that, nice and easy. Alpha 0 equals B over R. So just to remind you what it is I've calculated again, this is the angle a ray has to be launched into the system so that when it reaches this second element, it will be at the height of the radius of that element. So a ray put into the system from the axis at this angle will just hit the edge of that particular element. So all I need to do is calculate the matrix from here to the element, look at the B element of that matrix, divide it by the radius of the element, and that gives me the launch angle. So all I have to do if I want to find the aperture stop is do that for every element in the system. So I repeat that for every element in the system, finding the matrix up to that element, dividing its B element by the radius of that particular lens, and whichever gives me the smallest angle must be the aperture stop. So through that procedure you can calculate the aperture stop nicely. Calculating the entrance pupil is then nice and easy. So for instance, if this particular one, it's actually the last lens, which is the aperture stop, I want to just find the image of this in all the lenses that are before it, and that's what the entrance pupil is. So all I do is I do some optics to find an image distance from an object distance. So I calculate the matrix for these three lenses, the ones before the aperture stop. The object distance is then the aperture stop to the first of those lenses. And then I can use what I showed from last lecture to find the image distance. Excuse me. So that procedure works. One important thing though is that this matrix here we are calculating back in this direction. So you would do them in the opposite order. This would be the first lens, then this gap, then this lens, then this gap, then this lens. So you do that in that direction, it gives you the entrance pupil. If there were more lenses behind, we could calculate through those lenses to get the exit pupil. So the that's the procedure for finding the aperture stop and the entrance and exit pupils. How about the field stop? Well, the field stop is quite similar. We're again going to trace the rays through until they just hit the edge of each element. But this time we're going to start with rays which are on the edge of the object. So what we really want to know is how high up here can we get before the ray doesn't get through the system anymore. So we have a certain height and a certain angle. And the important thing for this angle is that the ray has to be angled to go through the entrance pupil. So we've already calculated the entrance pupil. Now we're calculating which ray off the axis gets through the entrance pupil, but also gets through all the rest of the system. So in order to do that, we can see that this angle, alpha 0, is actually going to be related to this height. And actually the tangent of that angle is going to equal how high up we are divided by how far away the object is from the entrance pupil. And that distance is irrespective of any lenses or anything in between. So if the entrance pupil was the other side of this lens, we'd still just take the distance from the object to the entrance pupil. So because we're using the small angle approximation, alpha 0, it actually equals h0 over L. And so our matrix calculation now becomes this. So our input ray is L alpha 0, and our output ray is R alpha 1. So now we do exactly the same process as we did before. We do this multiplication, and this time our angle equals R over AL plus B. So you can go through exactly the same procedure as you did before. You go through each individual ray, calculating the matrix up, each individual element, calculating the matrix up to that element, use the matrix to calculate the angle. Smallest angle is the field stop. You can then take that field stop and find its image in the preceding elements and in the after elements to find the entrance window and the exit window. So to summarize one last time, the aperture stop is the element in the optical system, the actual real element that limits the amount of light that can get through the system. Its images are the entrance pupil and the exit pupil, and the positions and sizes of those can be used to work out the field stops, but also how the rays are going to interact with other optical systems. The field stop is the actual element which limits the width of the field of view of the system. So how wide a field of view do you have when you form images with this system? How much of the scene can you capture? And the images of that stop, of the field stop, are called the entrance window and the exit window. Okay? So we'll leave it there. If you want some more information, the section of the book 3.1 goes into this in similar detail. They don't there talk about using the matrices to find them, but I think this approach kind of works quite nicely, and in your assignment you will have to use that approach to try and find the entrance and exit pupils of a similar system to this. Okay, thank you. We're going to leave it there, and see you next time.